I'm Takehiro Shimada from IHI Corporation in Japan. Today, I will present under the title of Micromechanics Modeling of Ceramic Matrix Composites, considering the probability of crack deflection. So these are the contents of my presentation. First, I introduce the background and objective. This graph shows the tensile loading tests of ceramic matrix composites, CMC. And we can see that the deformability and the strength, tensile strength is totally different, depends on the material. And the right picture shows the fracture surface of 3 specimens and the fracture surface of specimen C with the highest tensile strength shows the fibers are totally pulled out. And on the other hand, the fracture surface of specimen A with the weakest strength shows the surface is totally flat. This is because that the crack penetrates into the fiber without deflecting around the interface. And this happens when the interface strength is too high. So to prevent the composite failing in catastrophic and brittle manner, it is important that we understand the relationship between the fracture mechanisms and the interface strength. Next, I'll explain the calculation of crack deflecting probability. So the energy release rate of crack deflection is calculated from FEM analysis and utilizing virtual crack closure technique methods, VCCT. And CTC is the interface toughness, and which is the energy required for crack deflection. And this interface toughness is measured by push-in tests, showing this figure. And the push-in test is a testing method to obtain the interface strength by repeatedly pushing the fiber like this. And the energy release rate exceeds the interface toughness, the crack deflection occurs. And the same applies to the case of the crack propagation. And ZPC is the surface energy of fibers, and which is also the required energy for the crack propagation. And the energy release rate exceeds the surface energy, the crack propagates occurs. And considering which occurs earlier, crack propagation or crack deflection, the condition of crack deflection and crack propagation is written in these equations. So to calculate the energy release rate for the crack propagation or deflection, I conducted the FEM analysis. And the radius or thickness of fiber and interface matrix and elastic modulus is listed in this chart. And the boundary condition is shown in the left figure, and other analysis conditions are written here. I use the actual symmetric model and without considering large deformation. And my simulation is elastic analysis. So these are the results of FEM analysis. And the left figure shows the result with no crack deflection, and the right one is with crack deflection, which length is 0.05 micrometer, and the contour shows the bone mesocyst stress distribution. The strain energy is calculated by integrating overall elements, and the released energy, delta U, is the difference of these two values, UN and UD. And the crack deflection area, delta A, is calculated in here. So the energy release rate can be calculated like this. And the same applies to the case of crack propagation. And the area, crack propagation area delta A is calculated like here. So the value is slightly different from the one of the crack deflection. And from this FM analysis, we can calculate the energy release rate for the crack propagation and crack deflection. This graph is an example of the relationship between the energy release rate and strain. So we can see that the energy release rate increases as the strain also increases. And the energy release rate for crack propagation, the red line, plots, and exceeds the crack surface energy of fibers at this point, and the energy release rate for crack deflection exceeds the interface toughness at this point. So in the case of the above figure, crack deflection occurs before crack propagates. And the condition of crack deflection and crack propagation is rewritten in these equations. So this graph shows the relationship of the probability distribution of interface toughness GDC. So, and this data is obtained by pushing tests. And according to these equations, the crack deflection probability of material A is estimated over 90%, and crack deflection probability of material B is estimated from 30 to 40%. So the crack deflection probability changes significantly because the interface toughness also varies depending on the material. So next, I'll explain the simulation of tensile behavior of unidirectional composites. First, I'll explain the Sierra theory. According to this theory, even if the crack occurs in the fiber or matrix, the force is transmitted through the interface, and we can calculate the stress gradient of fiber or matrix from the equation of force balance between here. And the left figure shows the example, and it is in the case of one crack occurs in the fiber. And we can calculate the stress gradient like this. And considering much more cracks in the fiber or matrix, the overall stress distribution is calculated like in the figure in the right, like this. So we can calculate the stress distribution of the fiber and matrix. And based on the Sierra theory, if the interface strength is stronger, load transfer through the interface is more likely to occur, which increases the strength of the composites. However, when the interface strength is too high, the crack deflection probability decreases. So it makes it more susceptible to brittle fracture. So it is in trade-off relationship. This is a flowchart of proposed Monte Carlo simulation. And my proposed method is Monte Carlo simulation that can take into account the crack deflection probability calculated before. So these are the results of proposed Monte Carlo simulation. And this is a stress strain curve. And this is the condition of simulation is between this chart. And when the crack deflection probability is over 90%, the composite has sufficient deformability. On the other hand, if the crack deflection probability is 17%, the composites fail in a brittle manner. So next, I explain the comparison with experimental results. And the material A is estimated to have the crack deflection probability of over 90%. And this is the result of tensile loading tests of material A. And we can see the material A is sufficient deformability and has a sufficient tensile strength. On the other hand, the material B is estimated to have crack deflection probability of from 30 to 40%. The tensile loading test of material B is here, and the material B has poor deformability and it has very low tensile strength. From this, we are able to reproduce the tendency for the unidirectional composite to fail brittly. Finally, I conclude my presentation. The energy release rate was calculated based on the partial crack closure technique, BCCT. And the probability of crack deflection was estimated from the energy release rate calculated from the FM analysis. And Monte Carlo simulations, considering the probability of propagation, were proposed and conducted and reproduced the tendency for the unidirectional composites to fail brittly due to changes in the crack deflection probability. That's all. Thank you for your kind attention.